We're getting ready to start our next chapter on solutions. There's so many different variables and factors that are involved with solutions, and it makes them pretty fun to work with. Lots of good math in this unit. So a solution is a homogeneous mixture in which the components are uniformly intermingled. So homogeneous meaning we can't see different parts of it, so to the naked eye it all looks the same. And they're uniformly intermingled, meaning that there's not a higher concentration in a certain part of that solution. So terms, starting off the new unit with some terms. Solvent is the substance that's present in the largest amount in a solution. It's the substance that does the dissolving. 99% of the time, our solvent is going to be water. It's referred to as the universal solvent because it's used so often. It doesn't mean that it's the only solvent. And then solute is the other substance or substances in a solution. It's the substance that is dissolved. I like to remember that the solute is a smaller word, and the smaller word goes into the larger word kind of thing. So the solute is the smaller quantity that goes into the larger quantity. So in a salt water solution, salt would be the solute and water would be the solvent. Electrolytes are substances that break up in water to produce ions. That means they dissociate, just like we learned when we did reactions. We could see how different ions dissociated in our net ionic equation. These ions can conduct an electric current. So examples of things that can conduct an electric current are acids, bases, salts. Your ionic compounds, things that are made from opposite sides of the periodic table. Opposite sides of the periodic table tell us that they are ionic and therefore will dissociate. So, for example, our salt that we're familiar with, NaCl, in water, we sometimes write H2O over top of the arrow, will break into Na plus aqueous plus Cl minus aqueous. Solubility falls under this umbrella of something called like dissolves like. So polar molecules dissolve polar molecules, and nonpolar molecules dissolve nonpolar molecules. So polar molecules are things that have a partial positive or a partial negative. Water is a prime example. If we look at water, it's that bent structure. And we have sort of a negative side, which we refer to as delta negative, which means this side is a little bit positive. So polar things dissolve polar things. They also dissolve ionic things, so opposite sides of the periodic table. So our salts dissolve in water. Nonpolar molecules dissolve nonpolar molecules, and these are typically your covalent molecules. So these are a nonmetal plus a nonmetal. Just a quick refresher of our solubility rules, because obviously if things are dissociating and we have solutions, which things precipitate is going to come up again when we start looking at now doing stoichiometry with precipitate reactions. And so just as a quick reminder and a refresher, and we should have them in our notes so that we can refer to them in this unit. All common salts of group 1 elements, so our alkali metals, and ammonium, NH4+, are soluble. All common acetates and nitrates are soluble. All binary compounds of group 7, this is our chlorine, bromine, and iodine, with metals, are soluble except for those of silver, lead, or mercury. Those are our exceptions. And then all sulfates are soluble, SO4 - 2, except those of barium, strontium, calcium, silver, mercury, mercury 1, and lead. Except for those in Rule 1, carbonates, CO3 - 2, hydroxides, OH - 1, oxides, O2 - 2, sulfides, S - 2, and phosphates, PO4 - 3, are insoluble. And here's some terms. Another term that we use this unit is saturated. Saturated means a solution contains the maximum amount of solute. It has the most that it can possibly hold. So if I were to add more solute, it wouldn't be able to dissolve. So I can make saltwater solution up to a certain concentration, and then no more of it will dissolve. It will only hold a certain amount, and that's referred to as saturated. Unsaturated is when its solvent can dissolve more solute. So we have a saltwater solution that's not very concentrated, there's just a little bit of salt in it. We can certainly add more and dissolve more. Then we have supersaturated, and supersaturated is when the solution contains more solute than a saturated solution will hold at that temperature. So we trick the solution into dissolving more. The way that we do this is if we heat the solution up. So we heat up, we're talking about a saltwater solution. A certain amount of salt dissolves at, say, room temperature, 25 degrees Celsius. If I heat that solution up to 75 degrees Celsius, I can dissolve more salt. Temperature goes up, I can add more salt, depending on what salt it is. Then I very, 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 very slowly cool down the solution, and it doesn't crystallize out. If I cool the solution rapidly, it will crystallize out right away. But if I cool it very, very, very slowly, I can trick it into staying dissolved, and it's referred to as supersaturated. Concentrated is a relative term. Concentrated says a relatively large amount of solute is dissolved. It's only useful when it's done in comparison to something. So if you're talking about making lemonade with lemonade mix, and the recipe tells you to put 2 scoops per gallon of water, and you make 2 batches, and you make one with 3 scoops and one with 1 scoop, you can use the words concentrated and dilute with them because they're relative terms. You have something to compare it to. You can't really say that something is concentrated unless you have some sort of standard and comparison. Concentrated and dilute, although we use them fairly common in our regular lives, are not very useful to chemists because we need more specific information. We either want to know exactly how concentrated it is, or we want to use words like saturated, which means that there is a definite endpoint. Factors that affect the rate of dissolving, which means how quickly things dissolve. Ultimately, a solution at a certain temperature will only ever dissolve the same amount of substance. So surface area will affect the rate. If I put in a giant brick of chemical as opposed to a granulated form, the granulated form will dissolve much faster. However, they will both ultimately dissolve to the same concentration. The big brick of chemical will just take much longer. Stirring will also speed up my rate of dissolving. But it won't allow it to dissolve more, just speeds it up. So same thing is true. If I put, some sort of salt into a beaker of water and I didn't stir it and I just left it there, eventually it would be the same concentration as salt that I put in and stirred. And then temperature. Temperature will allow substances to dissolve faster, but will also change the solubility. Most substances have higher solubilities, meaning they can dissolve more at a higher temperature. Not all. Gases definitely decline as temperature increases, and there are a few solids that are actually more soluble at lower temperatures. And so we'll look at some experiments with that, and we'll also look at some graphs that explain that. Oh, and there's the graph we're going to look at, but we're going to look at that the next time. That's just the idea of looking at temperature versus solubility in the form of a graph.